The universe, vast and enigmatic, has always beckoned humanity to unravel its mysteries. For centuries, our understanding of the cosmos relied solely on the light that reached us from distant stars, galaxies, and cosmic phenomena. Telescopes, both optical and radio, have allowed us to peer deep into the fabric of space, revealing the birth and death of stars, the swirling arms of galaxies, and the faint afterglow of the Big Bang. Yet, despite these remarkable achievements, there remained a fundamental limitation. All these observations depended on electromagnetic waves. But what if there were other messengers capable of traversing the cosmos unimpeded by dust, gas, or intervening matter? What if we could for the first time listen to the universe as well as see it? The detection of gravitational waves has ushered in just such a revolution, offering an entirely new way to experience and comprehend the cosmos. Gravitational waves are ripples in the very fabric of space-time itself, predicted over a century ago by Albert Einstein as a consequence of his general theory of relativity. According to Einstein, massive objects like stars and black holes warp the geometry of space-time, and when these objects accelerate, such as when two black holes spiral towards each other and merge, they generate disturbances that propagate outward at the speed of light. These disturbances are gravitational waves. Unlike electromagnetic waves, which can be absorbed, scattered, or blocked, gravitational waves pass through matter virtually unimpeded, carrying pristine information about the cataclysmic events that generated them. For decades, gravitational waves remained a theoretical curiosity, their existence universally accepted by physicists, but their direct detection considered an almost insurmountable challenge. The reason lies in their extraordinary weakness. Even the most violent astrophysical events produce ripples that distort space-time by less than the width of a proton over distances of kilometers. Detecting such minuscule changes requires instruments of unprecedented sensitivity, technological innovation, and patience. This monumental challenge was finally overcome in September 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from the merger of two black holes over 1 billion light-years away. The signal, lasting a fraction of a second, confirmed one of Einstein's last untested predictions and opened a new era in astronomy. The announcement in February 2016 electrified the scientific community and captured the imagination of the public. For the first time, we had not only seen the universe but heard it, sensed its vibrations, and glimpsed events previously hidden from view. The detection of gravitational waves is not merely a triumph of experimental physics. It is a profound expansion of our senses. It allows us to probe regions of the universe that are otherwise inaccessible. Black holes, for example, do not emit light. They are invisible against the backdrop of space. Yet, when they collide, they send out powerful gravitational waves that ripple across the cosmos, carrying with them a detailed record of the event. By detecting and analyzing these waves, we can reconstruct the masses, spins, and orbits of the merging black holes, and even infer the properties of the space-time around them. The implications of gravitational wave astronomy are staggering. First, it provides direct evidence for the existence of black holes and neutron stars, and for the fact that they exist in binary systems capable of merging. Second, it allows us to test the predictions of general relativity in the most extreme environments imaginable, where gravity is so intense that it warps space and time to their limits. Third, it opens the possibility of discovering entirely new types of sources, such as the mergers of more exotic objects or even signals from the earliest moments of the universe itself. The technology behind gravitational wave detectors is as fascinating as the discoveries themselves. LIGO and its European counterpart Virgo use laser interferometry to measure infinitesimal changes in distance. Each observatory consists of two long arms arranged in an L shape, with mirrors suspended at the ends. A laser beam is split and sent down each arm, reflected back, and recombined. If a gravitational wave passes through the detector, it stretches one arm and compresses the other by a tiny amount, causing a change in the interference pattern of the laser beams. The precision required is mind-boggling. LIGO can detect changes in length smaller than 1/10,000th the diameter of a proton. Achieving this sensitivity requires isolating the detectors from every conceivable source of noise, seismic vibrations, thermal fluctuations, even passing trucks miles away. The mirrors are suspended by multiple pendulums in vacuum chambers, and the entire system is controlled with exquisite feedback mechanisms. The data analysis is equally challenging as the signals are buried in background noise and must be extracted using sophisticated algorithms and matched filtering techniques. Since the first detection, LIGO and Virgo have observed dozens of gravitational wave events, each one a window into a previously invisible universe. Most of these have been mergers of black holes, but in August 2017, a new milestone was reached: the detection of gravitational waves from the merger of two neutron stars. This event, GW 170817, was accompanied by a burst of gamma rays and was observed across the electromagnetic spectrum by telescopes around the world. For the first time, astronomers witnessed the birth of a kilonova, a brilliant explosion powered by the radioactive decay of heavy elements forged in the collision. This observation confirmed that such mergers are the origin of many of the universe's heaviest elements, including gold and platinum. The multi-messenger nature of GW 170817 marked a turning point. By combining gravitational wave data with electromagnetic observations, scientists could pinpoint the location of the event, study the physics of the explosion, and probe the behavior of matter at nuclear densities. It also allowed for an independent measurement of the Hubble constant, the rate at which the universe is expanding, providing a new cross-check on one of cosmology's most fundamental parameters. Looking ahead, the future of gravitational wave astronomy is bright. New detectors are under construction or being planned, including KAGRA in Japan and LIGO India. Upgrades to existing observatories will improve their sensitivity, allowing them to detect fainter and more distant events. In the coming decades, space-based detectors like the Laser Interferometer Space Antenna, LISA, will open up the low-frequency gravitational wave sky, enabling the study of supermassive black hole mergers and possibly even the echoes of the Big Bang itself. The potential for discovery is immense. Gravitational waves could reveal the presence of primordial black holes, relics from the early universe that may account for some or all of the mysterious dark matter. They could uncover new forms of matter, such as boson stars or cosmic strings, predicted by theories beyond the standard model of particle physics. They might even allow us to probe the quantum nature of gravity, bridging the gap between general relativity and quantum mechanics. Beyond the scientific implications, the detection of gravitational waves has a profound philosophical resonance. It reminds us that the universe is not static and silent, but dynamic and alive with motion. Space and time themselves are malleable, capable of vibrating in response to the dance of massive objects. Our ability to sense these vibrations is a testament to human ingenuity and curiosity, and a reminder that the cosmos still holds secrets waiting to be discovered. The story of gravitational waves is also a story of international collaboration and perseverance. The LIGO and Virgo collaborations involve thousands of scientists, engineers, and technicians from around the world working together over decades to achieve a common goal. Their success demonstrates the power of cooperation and the value of investing in fundamental research, even when the outcome is uncertain and the challenges appear daunting. As we continue to explore the universe through gravitational waves, we are likely to encounter surprises. The history of astronomy is rich with examples of unexpected discoveries: pulsars, quasars, cosmic microwave background radiation, all found by looking at the universe in new ways. Gravitational wave astronomy is still in its infancy, and its full potential has yet to be realized. One tantalizing possibility is the detection of a stochastic gravitational wave background, a faint, persistent hum produced by the superposition of countless distant sources, or perhaps by processes in the early universe, such as inflation or phase transitions. Detecting this background would provide unique insights into the conditions of the universe. Fractions of a second after the Big Bang, probing energies far beyond the reach of terrestrial particle accelerators. Another frontier is the search for continuous gravitational waves from rapidly rotating neutron stars or pulsars. These objects, with masses greater than the Sun compressed into a sphere the size of a city, can emit steady gravitational waves if they have asymmetries in their shape. Detecting such signals would shed light on the internal structure of neutron stars and the physics of matter at supranuclear densities. Gravitational wave detectors are also sensitive to bursts of unknown origin, short, transient signals that do not match any known template. These could be signatures of entirely new astrophysical phenomena, or even of processes associated with new physics. The openness of gravitational wave astronomy to serendipity is one of its greatest strengths. The impact of gravitational wave discoveries extends beyond astrophysics. The technological innovations developed for LIGO and Virgo have found applications in other fields, from precision metrology to seismic monitoring. The data analysis techniques used to extract weak signals from noisy backgrounds have influenced machine learning and statistical inference. The global excitement generated by the first detections has inspired a new generation of scientists and engineers, and has brought the wonders of the universe into classrooms and living rooms around the world. In reflecting on the journey from Einstein's equations to the first detection and beyond, we see a microcosm of scientific progress: bold ideas, patient experimentation, incremental advances, and sudden breakthroughs. The detection of gravitational waves is both an end and a beginning, the culmination of a century-long quest and the opening of a new window onto the cosmos. As we listen to the faint echoes of distant collisions, we are reminded that we are part of a universe in motion, shaped by forces that operate on scales both grand and minute. The ripples in space-time carry stories from the depths of time and space, inviting us to decipher their meaning and expand our understanding of reality itself. In the years to come, gravitational wave astronomy will continue to transform our view of the universe. It will deepen our knowledge of black holes, neutron stars, and the violent processes that shape galaxies. It will challenge our theories of gravity and matter, and may reveal new aspects of the cosmos that we have yet to imagine. Above all, it will remind us that the universe is not only stranger than we suppose, but stranger than we can suppose, a realm of endless wonder waiting to be explored.